Welcome to DAR Tutors. Today we will be covering hypothesis testing for the mean of a Poisson population, a key topic in the IB Applications and Interpretation higher level curriculum. By the end of this video, you will be able to 1. Understand how the Poisson distribution is used in hypothesis testing. 2. Calculate the p-value for a Poisson test statistic. And 3. Conduct a complete hypothesis test to interpret the results. Let's begin by establishing the context. In previous lessons, we primarily dealt with hypothesis tests for populations that were normally distributed. This allowed us to use tools like the t-distribution or z-distribution. However, many real-world scenarios are not continuous and symmetric. Often, we are counting the number of times an event occurs in a fixed interval of time or space. For these situations, the Poisson distribution is the appropriate model. So what are we testing? Suppose we have a population that follows a Poisson distribution. A Poisson distribution is characterized by a single parameter, lambda, which represents the average rate of occurrence of the event. Our goal is to test a specific claim about this mean rate. We formulate a null hypothesis, H0, which states that the true mean is a certain value, lambda naught. This is our starting assumption, the status quo that we want to test. To do this, we collect data. We take a random sample of n independent and identically distributed observations from this population. Let's call them x1, x2, all the way up to xn. Each of these observations, xi, is a count from the Poisson population with mean lambda. Now let's talk about the test statistic. To make a decision about the population mean lambda, we need a value calculated from our sample data. The logical choice is the sum of our observations, or something related to it. An important property of the Poisson distribution helps us here. The sum of n independent Poisson random variables is itself a Poisson random variable. Let's repeat that. The sum of n independent Poisson variables is also a Poisson variable. We can define our test statistic, which we'll call t, as this sum. So t is the sum of all our sample observations from x1 to xn. What is the distribution of t? Its mean, E of t, is the sum of the individual means. Since each xi has a mean of lambda, the sum has a mean of n times lambda. Therefore, our test statistic t follows a Poisson distribution with parameter n times lambda. This is a very powerful result because it means we can test hypotheses about lambda by testing hypotheses about t. And under our null hypothesis, H0, where lambda equals lambda naught, the test statistic t is distributed as a Poisson with parameter n times lambda naught. This is our null distribution. This null distribution, po n times lambda naught, is crucial. It tells us what kind of results we should expect if the null hypothesis is actually true. We'll compare our observed sample result to this distribution to see if it's too unusual to have happened by chance. Now that we have our test statistic and its distribution under the null hypothesis, our next step is to calculate the p-value. The p-value is the cornerstone of hypothesis testing. The p-value tells us the probability of observing our sample data, or something even more extreme, if the null hypothesis is true. A small p-value suggests our sample data is unlikely, which provides evidence against H0. The way we calculate the p-value depends entirely on our alternative hypothesis, H1. For this course, we will focus on one-tailed alternative hypotheses. Consider the case where our alternative hypothesis is that the true mean is less than our null value. That is, H1 is that lambda is less than lambda naught. If this is true, we would expect to see a small value for our test statistic t. Therefore, the p-value is the probability that our test statistic t is less than or equal to our observed value, t lowercase. So p-value equals the probability that capital T is less than or equal to lowercase t. Visually, this means we shade the left tail of the null distribution from our observed value t downwards. Let's look at the other case. If our alternative hypothesis is that the true mean is greater than our null value, lambda naught. In this scenario, if H1 is true, we'd expect to see a large value for t. So, the p-value is the probability that t is greater than or equal to our observed value, t lowercase. The p-value is the probability that capital T is greater than or equal to lowercase t. Here, we would shade the right tail of the null distribution from t upwards. An important point to remember for discrete distributions like the Poisson is to be careful with the inequality sign. The p-value is defined as the probability of observing something as or more extreme than the test statistic, so we must always include the observed test statistic in the probability calculation. Let's put all of this together into a structured process for conducting a hypothesis test. We can think of this as a 6-step plan. Step 1. State the hypotheses. First, define the null hypothesis H0, stating the value of lambda we are testing. Then state the alternative hypothesis, H1, which is the claim we are trying to find evidence for. So step 1 is to write H0 and H1. Step 2. State the significance level. This is the maximum p-value we are willing to accept to reject the null hypothesis. It's often denoted by the Greek letter alpha. A common significance level is 5%, or alpha equals 0.05. Step 3. Calculate the observed test statistic. This is the sum of your sample data. It's the total count of events in your sample period. Step 4. Calculate the p-value. Using the null distribution t is distributed as Poisson with parameter n times lambda naught. Find the probability that t is more extreme than your observed statistic t. This is the most computationally intensive step, often requiring a calculator. Step 5. Make a decision. You compare your p-value to the significance level alpha. If the p-value is less than alpha, you have enough evidence to reject H0. If the p-value is greater than alpha, you do not have enough evidence to reject it. Essentially, if the probability of your result under H0 is very small, you question the validity of H0. Step 6. Interpret your conclusion in context. This is crucial. Your final statement should relate back to the original problem, clearly stating whether or not the data supports the alternative hypothesis. You must explain what your statistical decision means in plain language. Let's work through an example from your textbook to see this process in action. We have example 7. The problem states, a sample of 5 observations is drawn from a Poisson distribution with an unknown mean lambda. The sum of the data values is 6. Is there enough evidence on a 10% level of significance to conclude that lambda is greater than 0.8? First, let's identify the key information given. The sample size, n, is 5, so n equals 5. The observed sum of data values, which is our test statistic t, is 6, so t equals 6. The significance level, alpha, is 10%, so alpha equals 0.110. And the claim we are testing against is lambda is greater than 0.8. This gives us our H0 and H1. This is a one-tailed upper tail test. We are looking for unusually large values of our test statistic. Step 2, the significance level, is given as alpha equals 0.10, so we can write that down. Step 3, the test statistic, is the sum of the observations, which is 6, so t equals 6. Step 4 is to calculate the p-value. First, we need the null distribution for our test statistic t. Remember, t is distributed as Poisson with parameter n times lambda naught. In this case, that's 5 times 0.8, which is 4. So, our null distribution is t is distributed as Poisson of 4. Since h1 is lambda is greater than 0.8, we are looking for large values. The p-value is the probability that our test statistic t is greater than or equal to our observed value, 6. So we need to calculate p of t greater than or equal to 6 for a Poisson of 4 distribution. This is a tedious calculation to do by hand. Fortunately, your calculator can find this for you. You would use the cumulative Poisson probability function, PCD, and find 1 minus p of t less than or equal to 5. This gives us a p-value of approximately 0.215. Step 5, the decision. We compare our p-value to alpha. We find that our p-value, 0.215, is greater than our significance level, 0.10. Therefore, we do not reject H0. Finally, step 6, the conclusion in context. Since we did not reject the null hypothesis, we cannot conclude that lambda is greater than 0.8. In other words, the sample sum of 6 was not large enough to be considered a statistically significant increase. Just a reminder, if you're looking for expert tuition in IB A-Level and IGCSE curricula, please contact DAR Tutors. You can find our contact information on our website. Let's work through another example. Suppose we are studying the number of defects on a roll of fabric from a particular manufacturing process. Based on historical data, the average number of defects per 100-meter roll is known to be 1.8. This gives us a historical average of 1.8 defects. A supervisor believes the process has improved, meaning the average number of defects has decreased. To test this, she takes a random sample of 8 rolls and finds a total of 10 defects. We'll conduct a hypothesis test at a 5% level of significance to see if the supervisor's claim is valid. Let's go through our 6 steps. Step 1 is to state the hypotheses. The historical mean gives us our null hypothesis. So H0 is that lambda equals 1.8. The supervisor's claim that the process has improved means the average has decreased. This makes our alternative hypothesis H1. Lambda is less than 1.8. This is a one-tailed lower tail test. Step 2 is to state the significance level, alpha, which is given as 5% or 0.5. Step 3 is the test statistic. The total number of defects found in the sample of 8 rolls was 10. So our observed statistic, t, is 10. Step 4 is the p-value. First, let's find the null distribution. It's Poisson with parameter n times lambda naught, which is 8 times 1.8 or 14.4. Since this is a lower tail test, the p-value is the probability of getting 10 defects or less if the true mean is 14.4. So we need to calculate p of t less than or equal to 10 for a Poisson of 14.4. Again, using a calculator's cumulative Poisson probability function for this, we find the p-value. The p-value is approximately 0.1. Step 5, the decision. We compare our p-value to alpha. Our p-value of 0.155 is greater than our significance level of 0.105. Therefore, we do not reject the null hypothesis. Step 6, the conclusion in context. We do not have sufficient evidence at the 5% significance level to conclude that the mean number of defects has decreased. The observed result of 10 defects could reasonably happen by chance, even if the true mean is still 1.8. So far, we've used p-values to make our decision. Another valid approach is the critical region method. The critical region is the set of all possible test statistic values that would lead us to reject the null hypothesis. In an upper tail test, the critical region is the upper tail of the null distribution where the cumulative probability is less than or equal to alpha. We call the first value in this region the critical value, C. If our observed statistic t falls into the critical region, we reject H0. Similarly, in a lower tail test, the critical region is the lower tail where the cumulative probability is less than or equal to alpha. The critical value C is the largest t in this region. If our observed statistic t is in the critical region, we reject H0. Let's revisit our first example using this method. The hypotheses were H0, lambda equals 0.8 versus H1. Lambda is greater than 0.8, with alpha equals 0.05. The null distribution was t is distributed as Poisson of 4. We need to find the critical region. For an upper tail test, we look for the smallest integer t such that the probability of t being greater than or equal to t is less than or equal to 0.05. We can calculate these probabilities using our calculator. P of t greater than or equal to 7 is about 0.11. This is still greater than 0.05, but P of t greater than or equal to 8 is about 0.051. This is also greater than 0.05. Let's check the next value. P of t greater than or equal to 9 is about 0.214. This is less than 0.05. This is our critical value. So the critical region C is the set of all integers greater than or equal to 9. Our observed test statistic was t equals 6. Is 6 in the critical region? No, it's not. Therefore, we do not reject H0. As you can see, the critical region method yields the exact same conclusion as the p-value method. It's just a different way of visualizing and making the same statistical decision. To solidify our understanding, let's work through a few practice problems in IB style. Remember the 6-step process. Practice problem 1. A bookstore claims that, on average, they receive 1.5 customer complaints per week. To check this claim, a quality controller monitors the bookstore for 4 weeks and finds a total of 9 complaints. Using a fat significance level, Test if there is evidence to suggest the true mean is higher than claimed. Pause the video here and try to solve this yourself. Then continue to see the full solution. Here is the solution. Let lambda be the true mean number of complaints per week. Step 1. Hypotheses. H0 is that lambda equals 1.5. The alternative is that the mean is higher, so H1 is lambda is greater than 1.5. Step 2. Significance level. Alpha is 0.05. Step 3. Test statistic. The total number of complaints over 4 weeks was 9, so t equals 9. Step 4. P-value. The null distribution is t is Poisson of 4 times 1.5, which is 6. The p-value is p of t greater than or equal to 9, which is about 0.0687. Step 5. Decision. The p-value of 0.0687 is greater than 0.05. Therefore, we do not reject H0. Step 6. Conclusion. At a 5-part significance level, there is insufficient evidence to conclude that the true mean number of complaints is higher than 1.5 per week. Here's our second practice problem. Practice problem 2. The number of typos on a page of a particular textbook follows a Poisson distribution. A publisher claims that the mean number of typos per page is at most 0.5. A proofreader checks 10 randomly selected pages and finds a total of 8 typos. Test the publisher's claim at a 1% level of significance. Take a moment to formulate your own solution before viewing the complete steps. Here is the solution. Step 1. Hypotheses. The publisher claims the mean is at most 0.5. The alternative, that which contradicts the claim, is that the mean is greater than 0.5. So H0 is lambda equals 0.5, and H1 is lambda greater than 0.5. This is an upper tail test. Step 2, significance level. Alpha is 0.001. Step 3, test statistic. The proofreader found a total of 8 typos on 10 pages, so t equals 8. Step 4, p-value. The null distribution is Poisson of 10 times 0.5, which is 5. Since H1 is greater than, we need p of t greater than or equal to 8. This is about 0.0681. Step 5, decision. The p-value of 0.0681 is greater than the significance level of 0.01. Therefore, we do not reject the null hypothesis. Step 6. Conclusion. At the percent significance level, there is insufficient evidence to conclude that the mean number of typos per page is greater than 0.5. The publisher's claim is not refuted. Let's try a problem that specifically asks for the critical region. This is our third practice problem. Practice problem 3. The number of meteorites found in a 1 square kilometer area follows a Poisson distribution with a mean of lambda. It is hypothesized that this mean is 12. A scientist believes the mean is actually lower than 12. He observes 1 square kilometer and finds 5 meteorites. Using a 10% significance level, A. Find the critical region and critical value. B. Using the critical region, determine if the data supports the scientist's belief. Part A, finding the critical region. Step 1, hypotheses. H0 is lambda equals 12. H1, representing the scientist's belief, is lambda is less than 12. This is a lower tail test. We need the null distribution to find the critical region. In this case, since N01, the test statistic t is just x, the number of meteorites found. The null distribution is Poisson of 12. So our critical region is the set of values t for which p of t less than or equal to t is less than or equal to 0.10. We'll use our calculator's cumulative Poisson function to check probabilities. Let's start from a lower value and work our way up. P of t less than or equal to 6 is very small, about 0.046. This is less than 0.10. P of t less than or equal to 7 is about 0.137, which is greater than 0.10. The critical value is the largest integer in our critical region, which is 6. The critical region C is the set of all integers from 0 to 6. Now for part B. The observed statistic was t equals 5. We check if it's in the critical region. Yes, 5 is less than or equal to 6. Therefore, the observed statistic falls into the critical region. We reject H naught. In conclusion, at the 10% significance level, there is sufficient evidence to conclude that the true mean number of meteorites in a 1 square kilometer area is less than 12. Our fourth practice problem is a bit more complex. It's similar to exercise 30G, number 2. Practice problem 4. To determine the age of archaeological specimens, scientists measure the emission of radioactive particles. The older a specimen is, the fewer particles it will emit. The number of particles emitted per minute follows a Poisson distribution with an unknown rate lambda. If a specimen is 5,000 years old, the rate is lambda equals 2. A scientist finds that in n equal 5 minutes, 9 particles were emitted. Test the hypothesis that the specimen is older than 5,000 years at a 5% significance level. This problem requires careful interpretation of the wording. Try to set up the hypotheses correctly. Let's work through the solution. Step 1. Hypotheses. The null hypothesis is our baseline, lambda equals 2. The scientist's belief is that the specimen is older than 5,000 years. From the context, this implies a lower emission rate. Therefore, our alternative hypothesis is that lambda is less than 2. So this is a lower tail test at alpha equals 0.05. The observed statistic t is 9, since 9 particles were emitted in the 5-minute interval. Next, the p-value. The null distribution is t is Poisson of 5 times 2, which is 10. We need to find p of t less than or equal to 9 for a Poisson of 10 distribution. Using a calculator, this p-value is approximately 0.4579. Step 5. Decision. The p-value of 0.4579 is much greater than our significance level of 0.05. Therefore, we do not reject H naught. Step 6. Conclusion. There is insufficient evidence at the 5% significance level to conclude that the specimen is older than 5,000 years. Notice how crucial it was to correctly set up the alternative hypothesis by understanding the context. An older specimen emits fewer particles. For our final practice problem, let's explore a common misconception. Why is the test statistic for a Poisson distribution always a non-negative integer? Practice problem 5. The test statistic. Question. In a hypothesis test for the mean of a Poisson distribution, explain why the observed test statistic must be a non-negative integer. This question tests your fundamental understanding of the Poisson distribution. Think about what a Poisson variable represents. Here is the explanation. The Poisson distribution models the number of times an event occurs in a fixed interval. A number of times, or a count, cannot be negative. You can't have -5 traffic accidents. Similarly, it's a count, so it must be an integer. It cannot be a fraction like 2.5 potholes. Furthermore, our test statistic is the sum of these individual counts. The sum of a collection of non-negative integers will always be another non-negative integer. That's why any observed test statistic in this context must be a non-negative whole number. This discrete nature is a key characteristic of the Poisson distribution. Let's quickly recap what we've learned today. First, we established the use of the Poisson distribution to model the number of events in a fixed interval with an unknown mean lambda. Second, we learned to define the test statistic t as the sum of n observations, and we discovered its distribution under the null hypothesis is p is in L0. Third, we saw how to calculate the p-value for one-tailed tests, ensuring we use the correct inequality for the discrete Poisson distribution. Fourth, we followed the 6-step hypothesis testing process to draw sound statistical conclusions in context. Mastering this topic is crucial for your IB exams. Remember, it's not just about calculating a number, but understanding what it means and how to apply it. Thank you for joining this lesson from DAR Tutors. If you need more personalized support to achieve your academic goals, please contact us for expert tuition in IB, A-Level, and IGCSE curricula.